Hey guys, so this video kind of runs through some of these notes we see here, but really also it's an overview of the quiz. It's not the sole video you should watch before you take the quiz. I would definitely also recommend watching things on the Doppler effect. Doppler effect. And you want to make sure you understand the differences and relationships between wavelengths and frequencies. Okay, so we'll touch on those a little bit in this video, but for a complete understanding, I would refer to the videos we've done throughout this week and last week. Okay, so this one primarily focuses on atoms and how atoms actually are able to emit and reflect light, right? Because really how we are able to get light is through photons being reflected, okay? We'll talk a little bit about that here. So we're going to talk about atoms, the electrons surrounding them. What kind of spectra do you see when you look at celestial objects? And that's actually going to pave the way for a lot of good research and studies that scientists are actually able to figure out what elements are found in stars and what densities that occupy the space between the star and the telescope you're looking at it from, what kinds of gas live there, right? And what we can learn from a star's spectrum. So we've talked about this before, but if we look at this diagram over here, atoms have electrons on different energy levels, and normally they exist on their ground state. So we've talked about how you have to fill your lower energy levels first before you can move up to the higher ones. That is always true when you're talking about the ground state of electrons. But when we get light, as we see here, light can actually be absorbed by electrons. And light is a form of energy that is going to excite that electron. So it's actually going to jump energy levels, okay, because it is absorbing energy. It's absorbing that light. So that electron actually jumps up an energy level, and we call that an excited state. An excited state has a lot of energy, but it is also not that stable. So it is going to get rid of its photon, and it's going to go back down to its ground state. And when it goes back to its ground state, it emits a photon, or also we can say releases a photon. That photon will have a certain wavelength, and that will be the color that you see. So plants, for instance, reflect. Plants are leaves and things that are photosynthesizing are green because the light that is being reflected is green, right? So whatever we see the reflected colors, because there are colors that are absorbed and there are colors that are reflected. They're two opposite terms, right? You can either absorb something or reflect it. What we see with our naked eye is the reflected light. So if all light is reflected, like if all spectrum of the light is reflected, that's how we get the color white. Let's see. I'm having technical difficulties. So, there we go. So we see white when all of these colors are reflected. When all of the colors are absorbed, that gives us the color black. Okay, so black is absorbed light, white is reflected. Okay, let's keep going. So, the motion of particles in a solid, liquid, or dense gas causes the emission of black body radiation. Basically meaning the things that exist between the star, where the light is coming from, and space, the gas particles in space, creates this radiation. Okay? And this is actually going to create a spectrum. The way I think about it, there's a star, and in between, as it emits light, there's all these gas particles found in space. And then we can actually, if we're like the person observing, we can actually, with certain technology and instruments, we can detect what these particles are. And will also tell us what colors are being produced. So this black body radiation creates this type of graph, and we can see we have frequency here, right? We can tell the frequency of the waves being emitted. We can also tell the intensity. And at certain intervals between 10 to the 14th and 10 to the 15th, we have our visible light spectrum. Okay, we can also see it at different intensity. It's also Kelvin. That's our temperature. So we are actually able to use this instrument as a celestial thermometer, where we can actually tell the relative temperatures of celestial objects, like stars. So the hotter an object, the more it radiates, okay? So an extremely hot sun is going to radiate more, right? That should kind of be intuitive, right? And the shorter the wavelength of maximum intensity. So if you recall, our shortest wavelengths of visible light is purple. Our longest wavelengths is red, right? And then there's all these colors in between. So extremely hot objects starts to emit colors closer to blue or purple than red. And because red kind of is what we think of, though. I know when we think of like fire, and when you're heating something up, it becomes red. There's actually temperatures hotter than that. Then we talk more like exponentially hotter, where we start to see blue, like blue stars and purple stars as like giving off an enormity of intensity. And this allows us to estimate temperatures of stars from their colors. So looking at some temperature scales, if we look at this top part here, hydrogen fuses at temperatures around 10 million, right? That's clearly a temperature we don't have on Earth. And this takes place in stars. Hydrogen atoms are constantly bouncing off of each other, and with enough energy, and if you hit it at the right angle, two hydrogen atoms collide, and you get helium. Right, you get two protons fused together. Okay, so that's going to just be, and then these elements also radiate or come out of the star. We can also see that water boils, freezes, and then here we have all molecular motion stops. This is called absolute zero, because sometimes we talk about temperature as being the average kinetic energy of particles. So when we have zero, like basically no energy, we have an object that is not moving, right? So that's absolute zero. We actually really can't observe something in absolute zero. We can get extremely close, like 0.00001 Kelvin, but not actually zero, because no matter how hard we try, particles are slightly moving. So this kind of gives us to our spectra, and we're going to talk about two different spectrums of light. And basically only certain energies are permitted in an atom. Photons of certain wavelengths can be absorbed and emitted. Okay, so each kind of atom has its own characteristic set of spectral lines, and we can use that to identify what the element is, or to identify unknown wavelengths and spectral lines. For instance, this model down here is showing sodium. Okay, and there's two different types of spectral lines that we'll see. All right, here's also, we have some more spectral lines of different elements. Hydrogen has very specific spectral lines. All of the elements have very specific spectral lines. That is kind of an identifier. Good way to think of it, let's see, it's kind of like a QR code or like a barcode, or like your thumbprint, right? it's a very specific identifier that lets us know what element we are looking at. And so that leads us to our bright line spectrum. If you look at a low density gas, so something that doesn't have a lot of particles, that is excited to emit protons, you see bright lines in the spectrum. Okay, and here we have like a bulb emitting white light. Some of the light goes through this slit. Here it enters a prism where it is refracting. Basically, it's bouncing around in here. And eventually it will project onto this screen, and it will basically diffuse and break up the lights so that we're able to see the light coming from the light, the colors coming from the light. Here we kind of have a black background, and here we have a heated hydrogen gas. So this is in a hotter environment. And this time we have what we call an emission spectrum, where we have a black background and we have lines of colors that are visible. In this case, red, green, and violet. So hydrogen is emitting these lights. It's refracting in the prism, it's bouncing around, and then it's emitted onto this screen. So if light passes through a low density gas on its way to your telescope, the gas absorbs wavelengths as it goes, and you can see dark lines in the spectrum, right? Such a spectrum is called an absorption spectrum. Okay, so this is with a cool gas. So absorption is cool gas. We talked just up here, emission, we have heated gas. That will be a question you might see on the quiz. Cough, cough. But here are the absorption spectrum. We can see these black thin lines. Those are appearing at the colors that are identifiers of, say, like hydrogen. So a spectrum can tell you basically the chemicals and molecules that make up the star, all of the elements in there. It's not just hydrogen and helium. The presence of spectral lines of a certain element shows that element must be present. But if the star is too hot or cool, the lines may be weak or absent, and they might be tough to pick up on. So it depends on the temperature of the star as well. So the strength of the spectral lines can tell you the star's temperatures. Okay, so if we look at this graph here, our hottest temperatures are up here, and then basically it's increasing as we go from the bottom to the top. But here you can kind of start to see as we have lower temperatures, we have things, the lines basically start to break up, and they're not as identifiable, right? Because that's just kind of all, it muddies the water a little bit. You don't have these crisp, clear spectral lines that you were hoping for. And we've talked in videos past about the Doppler effect, how basically the Doppler effect is completely based off of a source or an object moving past the source. It's all about motion and kind of relative. It's all relative, right? It all depends on where you are in relation to the object that is moving. So as things move towards you, if we look at this here at the bottom, so as something moves towards you, the wavelengths, it's high pitched, and then as soon as it passes you, it decreases and gets low pitch. You think about that NASCAR driving past, goes meow, starts high as it's getting close to you, and as soon as it passes you, it starts to decrease again. And we've talked about this also with stars. So when a star is approaching, you observe slightly shorter wavelengths. Remember, we talked about the shortest wavelengths, it's like purple. And in this case, we would see a blue shift. So we see blue, basically stars are emitting blue light. And that's if they are moving towards you. In this case, Earth. When it is receding, you observe slightly longer wavelengths, a redshift. And if you remember from the previous video, we observe most stars are red. So most stars are moving away from us, which is kind of evidence of the universe expanding, because everything is kind of moving away. They're getting more spread out, implying or suggesting that the universe is getting larger. And we can also tell a star's velocity. We can basically how fast a star is moving away from Earth. And last thing real quick, this is just a diagram of basically a star's shelf life. It exists in different temperatures, which we can see at the x-axis. And if we notice, it's hottest over here, and then it gets cooler as we go from left to the right. Our y-axis is showing intensity or luminosity, the brightness of this star. And this sequence, it's called the main sequence. You just see that kind of looks like the Milky Way or something. This is a common curve that most stars exhibit. They have their shelf life that starts here, and then it goes slowly. It gets cooler and cooler over time, and it also gets dimmer and dimmer. It's losing luminosity. And this is just another example of more specific stars as they go through this kind of shelf life. But that is the video. Let me know if you guys have questions. You have 2 attempts on the quiz, so take your time and make sure you are prepared. All right, see ya.